section 1.3, part 2. So we already discussed the differences about even, odd functions. Now we're going to verify if a function is even, odd, or neither algebraically. So for all of them, we start by finding f of negative x. So that means that for every x that we see here, we will substitute out the negative x. So negative x to the third power minus 6, and then we substitute with a negative x. Now we know that negative x to the third power is the same as multiplying negative x times negative x times negative x. And so for that, we know that from here to here, we will get a positive sign, but then a positive times a negative will give us negative, right? So we will have negative outside the parentheses, and then x to the third power. Here we will have negative times negative, that will give us positive, and 6 times x is 6x. Oh yes, thank you. Okay, so negative x cubed. Now we're going to compare it. So we will compare, is f of negative x the same as the original function? Is that the case? This is f of negative x, and this is the original function that I am referring to. Is it exactly the same? No. So this is a no, so we say they're not equal. Now let's compare f of negative x to the opposite of the original function. So remember, we want to make sure that every sign changed. And what I mean is, here we had a positive x cubed, here we have a negative x cubed, and here we have a negative 6x, and here we have a positive 6x. So would you guys say that this is true? Okay, let's write it down. So this is negative x cubed plus 6x. The original function is x cubed minus 6x, but I have this big minus here. So if I put that minus in front of it, and the function is inside parentheses, and I distribute it, I will get negative x cubed plus 6x. So now, can you guys tell me if this statement is true? Yes, it is true, right? So because of that, we say the function is odd. Okay, now let's try the next example. Okay, let's move to the next example, and we're going to do the same process. So we're going to find g of negative x. And same thing, we're going to substitute a negative x for every x on the original function. So negative x to the fourth power minus 2, and then negative x to the second power. So just to expand it here, negative x to the fourth power, it will be the same as negative x times negative x times negative x times negative x. And we know that if we multiply two negatives, we get a positive. If we multiply two negatives, we get a positive. So we know that if we multiply a positive and a positive, we should get a positive answer, correct? So then the answer for this problem, or that question, is positive x to the fourth power. Okay, now the next one, what I would like to do before distributing this negative sign, I would like to do the exponents first. So we know that negative x squared is the same as negative x times negative x. And so negative times a negative is a positive, so we will get positive x squared. Okay. And now finally, well, that's it. Okay, now let's compare it. Would you guys say that f of negative, I'm not sorry, it's not even called f. What is the name of this function? G. Okay. So would you guys say that g of negative x is the same as g of x? So the two that we are comparing is the one here, this is g of negative x, and then g of x is here. Are they equal? Yes, they are, right? They're exactly the same thing. So because of that, this condition is satisfied, and so we will say the function is even. All right. Now I want you guys to try the next one. Try it on your own, and then we will check our answer. Okay, so we have the answer for part C, and so we're going to check the following. Is h of negative x the same as h of x? No, right? It's not exactly the same as the original function, the original being here. Now we check the second statement to see if the function is odd. So is h of negative x the same as the opposite of the original? No, right? Because we have positive x squared, so we're good on that one. But then when we look at the second term, we have positive 2x, and here we have negative 2x. So that did not happen. I'm sorry, we're checking for opposite, right? Opposite. And then, well, anyway, so this happened. So this is the opposite. But then if you look at the other ones, they remain the same, right? So when you have some of your signs change, others didn't, then the function is even. Now let's check with the shortcut. If we look at the degree of every term, we have here an even degree. Here we also have an even degree because the constant term is of degree 0. However, here we have degree 1. So we have even degree, odd degree, even degree. Okay, so when you have those degrees mixed in your function, then you could assume the function is even. All right. However, on the exam, I still need you to do the whole process. Okay, no shortcuts, because I will just assume that you copy the answer from someone. Last year. Okay, let's go to the next slide. Any questions from this slide before I move on? Don't be shy. Okay. All right, now let's see how that translates even and odd functions. How will that translate into symmetry? Okay, and so when we have even functions, such as a quadratic function, we have here the equation for it. We could see that they reflect across the y-axis, meaning that if we were to fold this function in half across this line, we will get exactly the same thing, right? Now, 4 points, we have, let's start with the numbers. So we have, if we have the point 2, 0, we would also have the point negative 2, 0. So if you guys notice, they have the same y value, but the opposite x value. We also have here negative 3, 5, and we have 3, 5. So let's use that statement and check it with those numbers. So I'm going to let x be equal to 3. So Genesis. What is f of 3? You could just tell me the y coordinate. Wait, what? F of 3. So if 3 is the x, what will be the y value?
Both sides.
5. Okay, and then Leslie. I want you to tell me, what is f of negative 3?
Negative.
Oh, 5. So remember, we look at the y value, so it is 5. So is f of negative 3 the same as f of 3? Yes. Okay. Now let's do one more. Now let's let x equal to 2. And we're checking here. So, Lorenzo, what is f of 2? 0. So if the input is 2, the output is 0. Now, Chris, what is f of negative 2? Also 0. So they are the same, right? So that's kind of like where the statement comes from, and that's why it is useful to check algebraically. If f of negative x is the same as f of x, then you say the function is even. All right? That's why it works. And in general, if we look at this point, f of negative x is equal to y, and so is f of x, also equal to y. Okay? All right, Andrea, don't be texting. Okay, we're good. All right, now I'm going to just give you guys a very quick example. For those of you who took algebra with me last year, remember the decimals project? Yes? Some of you included some sine and cosine waves, and I was very proud of you guys because we had not discussed that. These are two functions that we're going to cover next semester in Precalc 2. So the function for cosine, the graph looks like this. And of course, it extends. So would you guys say that is odd or even? No, it's actually, it is even. Maybe it's not a good picture, but it is even. It is reflected across the y-axis, and moreover, I don't want to get into that, but if we were to pick two x values that are reflected across the y-axis, that will have the exact y value. Okay, moving on. And I'm showing you that because I want to point out something related to calculus in a minute. Now let's look at odd functions. And if we say that even functions are symmetric with respect to the y-axis, you might want to highlight that or something. If you have to make a guess, would it be okay for me to say that odd functions are symmetric with respect to the x-axis? Think about it. Why not?
Can you repeat the question?
Okay. Is it okay if I say odd functions are symmetric with respect to the x-axis?
No.
It's not okay. If I ever say that, please correct me. Because what I'm saying is something like this. That's symmetric with respect to the x-axis, right? But is that even a function? It's not a function, so no. If there are functions that will never be symmetric with respect to the x-axis, okay? So don't get confused by that. Odd functions are going to be symmetric with respect to the origin, okay? And what we're going to do here is, graphically, you can see from the graph, we have this point here, 2, 8. And so if we reflect that across the origin, you guys see how both of the signs change, the x and the y, okay? So let's write them down. So we have, let's let x be equal to 2. So we're going to find f of negative 2. What is f of negative 2, Yvette?
Negative 8.
Negative 8, very good. Okay, and now for this one, I want to find, let's ignore this negative first. Let's just find f of 2. What is f of 2?
8.
Emily, what is f of 2?
8.
8. Okay. But now, I don't want to compare it to the original function because I'm testing to see if the function is odd. So what I need is the opposite of that, right? So what is the opposite of 8? Negative 8. Now, is this true that they are equal? Is it true? Yes, right? Negative 8 and negative 8. Yeah? Okay, let's do one more. I'm going to pick this point and this one. Okay, so let's see. We're going to let x be equal to 1. So, Biryani, what is f of negative 1? Eyes on the board.
1.
Not positive
Oh,
for this
-1.
point right here.
-1.
-1, thank you. Okay, and now, Andrea, tell me what is f of 1? +1, very good. Now, we don't want to compare it to that. We want to compare it to the opposite of that one. Remember? The opposite. So, the opposite of 1 is -1. Now, can we say that these two numbers are equal? Yes, they are equal. So, what it means is that it satisfies this condition, f of -x is equal to the opposite of f of x. Okay? So that's how you could test numerically, graphically. And the previous slide we tested algebraically. Okay, now before I go to the next slide, question. Who sits behind you, Chris? Well, you don't know. No one? Okay, Gabriel, let's move next slide. Please. And are you okay back there?
Yeah.
All right. Andrea, you okay? Or do you want to move next to Raquel? You're okay? All right. Anyone who would like to move closer? No? Okay. So let's go to the next slide. Okay. Oh. Okay, example number 3, we're going to talk about piecewise functions, and the problem that we have here, I don't have the whole statement, but I can tell you what the problem is about. It describes a cell phone plan, and I believe that was talking about the minutes used, and I think this problem is kind of outdated, right? Because we don't really care about how many minutes we use on our cell phone. Most of us have unlimited, right? Yes. Yes. Sorry. All right. So what this is telling us is that the price for the cell phone plan, maybe it's a disposable one, it is $20 if you use anywhere from 0 to 60 minutes. Now, if you go over 60 minutes, you will have to pay 40 cents for every minute that you go over. Okay? So let's say that Miguel, he uses 100 minutes. To be honest, I use more text than minutes now. Yes?
So it was $20 if you stay under 60 minutes?
Yes. Or exactly at 60.
And it's 40 cents every minute after that, right?
Yes. So, Chris, how many minutes did Miguel go over?
30, 40. No, wait a minute, what?
So if he was allowed to use 60 minutes and he used 100, how many minutes did he go over?
40.
40, right?
40.
So 40 minutes over. So now, Sean, do you think Miguel will get charged for 40 cents for every single minute from here or from here? From the second one, right? So only the ones that he went over. Okay. So because of that, you guys see this function here? All right, so that's a piecewise function, right? We have it separated into two pieces. So the first one is pretty easy. Whatever, if your minutes are from 0 to 60, you only pay $20. Plus tax, of course. But if you go over, you get charged. And this little part here, that's where they subtract the minutes from the 60 that you're allowed to use. Yes?
I'm trying to figure out if it's cheaper to go over minutes than just to pay for the plan, actually, because I think it's actually cheaper.
Okay, sure. Thanks for asking. Okay, so, okay. So let's answer the first question. if you use 30 minutes, how much would you pay, Adelina? Remove your head. I'm sorry? Well, I know it looks like there's a 1 there, but it's actually just a 20. Can you believe that? I know those plants are pretty cheap, right? So 20. So $20. Same thing if we were to use 1 minute, it will still be $20. Because 1 or 20 or 30 or 15, they all fall between this interval, right? From 0 to 60, including 0, including 60. That means like if you were to not use your phone, you will still have to pay 20. If you were to use 60 minutes, you will still have to pay 20. Now let's see what Miguel is going to pay. And so Miguel, we already know we're 100, it falls in this interval here, right? 100 is bigger than 60. So we will have 20 plus 0.40 times 100 minus 60. And then we know that this will be 20 plus 0.40 times 100 minus 60 is 40. Remember, that was the answer that Sean gave me. And then if we multiply that,
It's 16.
16?
Yeah.
So 20 plus 16 is?
36.
36. Okay, so which one is cheaper, Chris?
I did it in like value of 60 instead of 30.
Oh, okay.
It's like I was trying to figure out if it was cheaper to just like go with the plan and pay $20 for 60 minutes, or if it was cheaper to pay for each minute individually.
Oh, okay. So you were thinking that the 60 represented the amount of money that the person was going to pay?
No, I knew that 60 was the amount of minutes you got, but I was
Oh.
like 60 minutes for $20 versus 60 minutes each minute separately. And it is cheaper to go with the $20 plan, because otherwise you'd be paying $24 for each minute.
Okay.
I'm just trying to make sure that cell phone bill isn't a rip, that's all.
Oh, okay. Well, most of the time it is. Yeah, I need to update this problem. Maybe something about how many gigs you get. That would be more interesting, right? Okay. All right, so next year. Next year. Okay, so next one, we're going to do the other piecewise function. And I just want to point something out. And you will have a question like this on your test, definitely, where I will give you the function, I will give you the intervals. Here we have 2 intervals. On the test, you might have more. You might have 3 or 4 intervals. And so the first thing that you need to ask yourself is like, which is the interval that my input falls into, okay? For example, the cell phone plan, we only had 2 options, right? So when you talk about piecewise functions, you can only use one interval and one interval only. Remember the definition of a function? For each x, there's only how many y's? Only 1. Okay, so I have students that, for example, if I ask them a question like, find f of 2, and so if I ask you that, will you guys use the first interval or the second interval? Is 2 less than 1, or is 2 greater than 1? Greater than 1, so we use the second interval, right? So the answer will be 4. And that's it. You're done, okay? There is no need to substitute it into both equations, because if you give me 2 answers, like let's say you want to do it for both intervals. Ezekiel, are you okay? If you do it for both intervals, you will get, oh wow, you get also 4. That's not a good example. Let's select another number. Let's say f of 1. Oh, that's a good one. What would you guys say? Should I select the first or the second interval? The first, right? Because we have that equal part here. Right here. Okay, so if I do that, I will substitute the 1. So it will be 1 plus 2, which is equal to 3. This is the correct answer. Nothing else, okay? I had students in the past, not at this school, at another school. I don't want to say the name. is not a high school. Where they do it twice, and so they give me two answers. This is wrong, okay? Oops. Wrong. Because what they're saying is that 1, 3 is a point, and so is 1, 4. But that statement contradicts the whole definition of a function. Each x has only one and one partner, not two. Okay, so please don't do that on the test. Now, what we're going to do here is graph the function. We're not going to answer any numerical questions. So we know that the first interval, it represents what type of function will this be? When x is to the first power, what is it? Gabriel. Well, yeah, it is. Well, in this case, actually, Dima, this is a good example. Yes. It's neither. But that's not what I was asking. This was shifted 2 units up. So it will look like something like that. That will be an example of something that is neither. Because the exponent here is odd, and this one is even. Okay? But if we were to do the f of negative x, we would find that there. What I was asking you guys, going back to the question, is the type of function that we have here is linear. Right? We've been talking about that function since Algebra 1. So what would be the y-intercept for that, Brianna?
I don't know.
Yes, you do. So you just got to think a little bit about it.
The y-intercept? Maybe 0?
No.
I don't know.
Okay, so let's think about if it is on the y-axis, tell me. Those. Okay, 2. And how do you know, Ezekiel? So maybe, do you remember the equation that looks like this? Oh. Mx plus b, yes. Mx plus b, right? That is the slope, and that is the y-intercept. Okay, so if I take this piece of the function, x plus 2, then the y-intercept will be 2, right? But as a point, if it is on the y-axis, what should be the x-coordinate here? 0. So the y-intercept as a point is the point 0, 2. Thank you, Ezekiel. So 2, 0, right there. I mean 0, 2. All right, what is the slope of that function? Remember, the slope is the coefficient of the x? 1. So the slope is a 1. And if I wanted to represent a rational number, so that would be like 1 over 1, right? So what does that mean in terms of going up, going down, going right, going left?
Don't you go like up and then right?
Very good. So the rise of a run will be you go 1 up and 1 down. I'm sorry, no, right. What am I thinking? 1 up and 1 right. Thank you, Beth. 1 up and 1 right. Okay. Now I could do the following: 1 up, 1 right, 1 up, 1 right. However, if I do that, well, maybe I could do it once. 1 up, 1 right. Right there. If I do it again, then I will be going outside of the interval, right? Because this one says values, x values that are less than 1 or equal to 1. So I don't want to do that. However, there's something I could do. What's another way to represent a positive 1? You could,
Negative 1 squared?
well, that's a good one. But as a fraction, negative 1 divided by negative 1. Negative 1. So we could also say that. Negative 1 over negative 1. And so if we use the y-intercept again, in this case we will go 1 down, 1 to the left, 1 down, 1 to the left, 1 down, 1 to the left, One down, one to the left. And you can keep going, but of course 2 or 3 points are good enough. Now we're going to extend, connect the points, and then should I stop here or have an arrow?
Arrow.
Because we're only saying numbers that are less than 1, right? So those could go to negative infinity. Now the second part of the function is here. What type of function is that? Constant. Thank you, Jose. So this is a constant function. We also know it as a horizontal line. Okay. And so that means that it doesn't matter what the x value is, the y value will always be 4. That's why it's constant, right? Okay, now that interval goes for values that are greater than 1. So then from here to here, we will have a horizontal line right at 4. However, for x equals 1, should we have a closed circle or an open circle? Open. Open. And then it extends. We're just saying values greater than 1, so they go to infinity. Okay, that's why we have the arrow.
I used to be really good at figuring out
Those things?
I can't remember
Some piecewise functions are called step functions because their graphs form of discontinuous steps. One such function is called the greatest integer function. And so we could symbolize it by int of x, or we could use this. It almost looks like, you can't really see it on your paper, but it's like a double bracket. Yep, that's what it is. So now let's go ahead and write down the definition for that. So whenever you have a function, okay. So a function like the greatest integer of x please write this down, all of you. So that is the definition, the greatest integer that is less than or equal to x. Okay, and before we get into the examples, I want you to do the following. I want you to label your horizontal and vertical axis by 2s. Go by 2. So meaning 2 squares, that will be 1. Then 4 squares, that would represent 2. 6 squares, that would represent 3. The reason I want you to do that is because if we don't, we're not going to get a very good picture. So this way, we have -1, -2, -3. So just take 2 squares per integer. Yeah?
Those are the top ones.
Yeah, well, so the top and the bottom. So 2 squares, that will be +1. 2 squares, that will be +2. +3. +4. Okay, now let's do some examples. So if I ask you the greatest integer, what is the greatest integer of 1? That is very simple to answer because the input 1 is an integer itself. So the answer will be the same integer, okay? That's what would come here, the part equal to. So the answer is 1. Same thing if I was to ask you, what is the greatest integer of 2? The answer will be 2, okay? Let's plot those points for now. So the point 1, 1 and 2, 2. Now let's see what happens in between those two integers. So if I ask you, what is the greatest integer of 1.5. So we look at the definition, and I want you to focus on this part. That is less than. Okay, so I want you to tell me what is the closest integer to 1.5 that is less than 1.5? 1. Very good. Not 2, is 1. Okay, if I ask you, what is the greatest integer of 1.9? What would you say? Is it 1 or 2?
1.
It is 1, because we're looking for the integer that is less than. I know that 1.9 is closer to 2, but we want it to be less than. Okay, so in other words, on the left side. And so that will be also 1. So for this whole interval here, it will be a horizontal line. Now, what should I do here? Leave it like that, or should I include something there? Like
Open circle.
open circle, very nice. Open circle. Now, what's happening here? What is the greatest integer of 2.3? So we're looking for the integer that is less than 2.3. What would that be, Yvette?
Wait, I don't get it.
Okay, so going back to the definition, whenever your input, the number inside the parentheses or your x value is an integer, the answer will be the same integer. Okay? Whenever we have a number that is not an integer, then you're going to look at the closest integer that is to the left side of it.
So 2?
Uh-huh. This
Okay.
will be 2. And I gave you the example of 1.9 because I know that 1.9 is closer to 2, but we don't care about that. We care about closer but to the left. And that's where the less than comes into. Okay? That part of the definition. Okay, so now 2.3 we get 2. Now let's check what will be the greatest integer of 2.79. What would that be? 2. Also 2. So then we have another horizontal line here. And then open circle, because the function value at 3, the greatest integer of 3 is 3. So when you get to x equals 3, the y value will be 3. And so that is the step function or the greatest integer function. Now let's do a couple of examples with negative numbers. Okay, so what is the greatest integer at 0 of 0? Is 0 an integer, Lorenzo?
Yeah.
Yes. So the answer will be?
What?
So if the input is an integer, the output will be the same as same. So it will be 0. Okay, Samantha. I asked you, what is the greatest integer of... okay, before we get to the negative numbers, let's try this one. 0.8. Remember, we want it to be less. Well, a little bit more. So we're here, we already plot that point, and then I gave you the x value of 0.8. So somewhere around here. So should I pick my y value to be 0 or negative 1? 0. So that will be the closest one. If we pick negative 1, then we will not be taking the closest, but one further. All right, so here we will have another step. Now let's do a couple of examples with negative numbers. So the greatest integer of negative 1 is an integer, right? Integers could be negative. So Raquel, what would be the answer here? So if negative 1 is an integer, the answer will be also an integer. So negative 1. Now the next one. The greatest integer of negative 1.6. So remember, we want to get an integer that is less than negative 1.6. So is that negative 1 or negative 2? Negative 2. Okay? And remember, negative numbers, the further you get from 0, the smaller they become, right? Okay. So the step pattern, it repeats over and over. And this is another question that some students that are taking calculus have been coming to us, like from that function. So don't think that this function is going to disappear. You will see it again. Okay, now let's go ahead and answer the word problem that we have on the bottom. Maybe it will make it a little more meaningful to you.
Miss Stephanie,
Yes.
I have a question. How do you know when to like put that the not included circle?
Oh,
How do
okay.
you know where to end it?
Well, because, for example, here, when we started at 1, we have to have the point 1, 1. Now, for 2, for x equals 2, remember I said if the input is an integer, the output will be the same integer. So I knew that the point was going to have to be 2, comma 2.
No, but I'm talking about the like the.
That I have open and close?
No, what like how do you know where to end the open circle?
Okay, so for that function will be until you hit the next integer to your right. And the reason I have open and close is because if I was to do the vertical line test, would it pass? Yes,
Yes.
because it's only touching this one. That one is not included. So that's why we have to have those open and closed circles. Okay? All right, let's go ahead to this problem. So this is something what I was talking about the other day about mailing a package or a letter in this case. And so if you mail a letter and the independent variable horizontal axis here, it represents the weight of the letter in ounces. And the vertical axis represents the cost of mailing that letter in dollars. So if the letter weighs between, well, no letter should weigh 0 ounces, right? But let's pick a small number, maybe something like 0.1 ounce. If your letter goes from that to 1 ounce, you're still going to pay 45 cents. Okay? If your letter is more than 1 ounce, but no more than 2, then you will pay 65 cents. Okay? So let's see if we can answer those questions. So f of 3, what does that mean in terms of the variables? So your independent variable is a 3. So Jonathan, what does that mean? You weren't paying attention? Okay, well, let's think about it. The horizontal axis is the independent variable, and that's the weight in ounces of the letter. The vertical axis is the cost in dollars. So f of 3, that is my input independent variable, is a 3 there. So what do you think that means? So what does this mean, the question? Okay, so 3 is the weight. Very good. And what else do you say? Oh, okay. So the letter weighs 3 ounces. And we want to find what is the cost. So how much would it cost, Jonathan, if the letter is 3 ounces?
85 cents.
85 cents. So Jonathan is looking at this point on the graph. Very good. 85 cents. So we could say that the question, what it means is that what is the cost of mailing a letter that weighs 3 ounces? And the answer is 85 cents. You may word it as however you want. The answer is 85 cents. 0.85 or 85 cents. Okay, now find f of 3.5. Let's see, what does that mean, first of all, Peru? Okay, so a letter that weighs 3.5 ounces. And how much would that cost? Very good. And so it was looking at the function value here, this point. So if the weight is 3.5 ounces, the cost will be 105, right? $1.05. Someone told me yesterday 105 cents. That's correct also. All right, next question. What is the cost of milling a letter that weighs 1.5 ounces? Crystal. 65 cents. Very good. So 1.5 ounces, we're looking at this point here. 65 cents. And what is the cost of milling a letter that weighs 1.8 ounces? Yaren? 0.65. Very good. Or 65 cents. Okay, so you guys see the greatest integer function is actually very applicable to real life, right? Even if you don't know things. All right, let's go to the next one, and I don't want to scare you, but this is not everyone's favorite thing to do. However, if you have good algebra skills, it will be okay. And so this is called the difference quotient, and you guys know I like to talk about calculus, so that's kind of like how calculus starts, okay? Taking the limit of that as h approaches 0, right? So, it's one of the bases for the derivative. So, I don't want to talk about it right now. So, what we're going to do is just kind of practice, because this class is called pre-calculus, right? We're supposed to be preparing you guys for calculus. So I don't want to do this part. I would like to just do the whole thing at once. And remember how the other day, I'm going to write this on the dry erase board, we were finding things like find f of 2. You know that you have to substitute a 2 for every x, right? We were also doing things like find f of x plus 3. And you knew that you had to substitute every x with x plus 3. We've been practicing how to do things like f of negative x, we know that. We also know how to do the opposite of a function, right? When you change the sign of every term. Okay, what we're going to do here is find f of x plus 8. Then we're going to take the opposite of the original function. And all of that will be divided by h. Now, why are we saying that h cannot be 0? I'm sorry, Sebastian? Can't divide by 0. Thank you. So, let's get started. Okay, and this is a function that we're going to consider. So for this x and this x, we're going to substitute that with x plus 8. Okay, so first I have a 2, it's part of the function, and then there comes the x. So I need x plus 8. Now the function has a square, so that goes here. And then we need minus, and then there comes another x, so we need to substitute that with x plus 8. And then finally, we have a plus 3. Okay, that's it for that one. Then we're going to need a negative, and then we're going to include the original function, that's what I have here, f of x. And so, Gabriel, what would be the original function here? Wait, that's too easy.
What portable is this one for?
It's portable 3. So I'll ask you, you're next on the next question. 2x squared minus x plus 3. That's the original function, right? And keep in mind we're dividing all of this by 8. Okay, now we're going to expand the binomial x plus h squared. And when we do that, please keep in mind that we are multiplying x plus h times x plus h. So if we distribute, we will have x times x, that is x squared, and then x times h, that will be xh, and then we have h times x, that will be xh, and finally we have h times h, and that will be h squared. Now we combine the two terms in the middle, we will get 2 times xh, correct? Okay, so I'm going to write that down here. Don't distribute the 2 yet. So we got x squared plus 2xh plus h squared. Now you guys see this negative sign here? Yes? So that one, we're going to distribute it. So we will have minus x minus h. Let's not forget about the plus 3 here. Okay, and now the same thing with this negative, we're going to distribute it. So we will have minus 2x squared, and then plus x, because we have negative times negative, and then finally minus 3. Remember, I will be posting this video, so if you want to watch it again, you're free to do so. Now I'm just going to write with one color, and I'm going to distribute this 2 now. So we will have 2 times x squared, 2x squared. Then 2 times 2xh, that will be positive 4xh. And then we will have 2 times h squared, and that will be plus 2h squared. And then we have minus x minus h plus 3 minus 2x squared plus x minus 3. We're almost done, I promise. Okay, now look at it and tell me if you find some terms that are opposites.
Will the 2x squared cancel out?
Yes, because they're opposites, right? So 2x squared minus 2x squared cancels out, that gives us 0, right? What else? Plus x minus x. Good. What else? Okay. And that's it. So 4xh plus 2h squared minus h. Now, if we look at every term from those 3 terms on the numerator, and when I say 3, I'm referring to 1, 2, and 3, right? What do they have in common? So, could we factor that out? Yes. So, if I factor that out, I will get 4x, okay? Two h. Yes. Okay, let's make sure. So if I factor 2xh, if I factor out an h, it's like I'm dividing by it, so I should have 4x. The next one, if I have 2h squared and I factor out an h, it's like I divide by it. So remember, we subtract the exponent, so we should get 2h. So that's that one there. How about the last one? We have negative h and we factor out an h, so that will be what? Negative 1. Negative 1, that's 0. We're dividing. So minus 1. Okay, I'm going to erase this. And let's not forget that everything is being divided by h. Now, the whole reason for that was that I wanted to divide or cancel this here. So h divided by h, that gives me a 1. So my final answer will be 4x plus 2h minus 1. Okay. And so that is the last problem for this section. I'll leave the other one for you. But what I'm going to do is make a short video of the next example, and then I will post that one in case you want to watch another one. Okay? So this is the end of section 1.3.